Log on, tune in, find out. Another good idea from Cambridge.
Very much. It's a pleasure to be here. So I'm John Schotland from the Mathematics Department at the University of Michigan in Ann Arbor, and I'm going to talk about one of the things that Simon didn't get to talk about. It's on his list of hybrid imaging modalities, not to be confused with photoacoustic imaging, or even optoacoustic imaging. I'm going to be talking about acousto-optic imaging. So there's thank you so much, Bill. It's a long list of combination modalities of imaging. It's the same generation. Perfect. Okay, so I like very much what you said, Simon, that optics is not straightforwardly used in medical imaging, and I couldn't agree more. Okay, so let me begin the story by talking about optical tomography, a topic which is very near and dear to my heart. Optical tomography is a sort of classic inverse boundary value problem in which you try to recover the coefficient of a PDE from boundary measurements, and it is often used, as shown in this slide here, for imaging of the breast, optical mammography. So here we have a patient, and the patient's breast is illuminated by light which is usually in the near IR part of the spectrum, brought to the patient, in this case, by optical fibers, and then detected by an array of optical fibers. And with a gadget such as this, it is possible to make the following kinds of reconstructed images. So these are images of two different patients with two different kinds of breast cancer. So these are craniocaudal slices through the breast, here and here. And these regions of enhancement correspond to the tumor. So these are images of the total hemoglobin concentration within the tumor and the blood oxygen saturation, that is the fraction of hemoglobin that has oxygen bound to it. And what you're supposed to take away from these images is that the resolution is relatively low, but as Simon says, there is access to contrast which is not typically available in more conventional imaging modalities. Okay, and that information can tell you about physiology and about derangements of physiology. Now, there are ways to, in some sense, improve the resolution of optical mammography, and this is a popular approach nowadays. It's called non-contact imaging, and the fiber optics are eliminated in favor of through-space optics on the source side, so a narrow collimated beam which can be steered from point to point by a pair of mirrors, and the light then exiting the sample being imaged onto a CCD chip. So this gives rise to many more orders of magnitude of data, and with very fast algorithms, it is possible to make reconstructions of these large data sets. It's a topic for another time. But here's an example of a reconstruction that can be done this way, using the so-called radiative transport equation to describe the propagation of light, and it's a slice of a lemon. I don't know if you can see very well back here. Again, it's just as Margaret said, the pictures don't look so great on the screen, but you can see the septations, and there are some seeds and so on. These images are comparable in quality, I would say, to the earliest MRs that were done also of lemons about 1980 or so. So even though the results are rather modest, there are good reasons for this, and they are, of course, mathematical. So let me begin the mathematical part of the talk by reminding you of the so-called diffusion approximation, which is the sort of standard model for the propagation of light in a random medium such as tissue. So here the energy density of the light obeys a diffusion equation. It's in fact it's an approximation. It arises as an approximation to the radiative transport equation. So d here is the diffusion constant of light, which is taken to be constant for simplicity. Alpha is the absorption coefficient of the medium, which varies from point to point. And then we must impose boundary conditions. Okay, so here these are chosen to be of mixed type, of Robin type, and on the right-hand side we have the source. Okay, so the forward problem then says to prescribe the source G and then calculate the light which exits the medium. The intensity of that light is then proportional to the energy density U. And so there is associated with this a map, which is sort of the analog of the Dirichlet-Neumann map. It sends inputs to output measurements on the boundary. And the inverse problem, of course, is to run this map the other way around, right? Is to recover the coefficient alpha from knowledge of the map from all possible source detector pairs. Okay. So then it's well known and follows from work of Sylvester and Ullman and Alessandrini that this is a severely ill-posed problem. There are unique solutions, but the solutions have at best logarithmic stability. They have a logarithmic modulus of continuity. And so this is what's behind all of the blurriness and so forth of optical tomography. So maybe there's a way around some of these issues. And this comes, now comes the idea of hybrid imaging. Okay. So the idea here, and this is, by the way, is a topic which is receiving a lot of attention right now, and there will be, as I understand it, a special issue of inverse problems devoted to it. So the idea is to achieve a higher resolution requires some kind of new physical approach. And so in hybrid imaging, we typically make use of two wave fields. So one gives you the high spatial resolution, the anatomical information that you would like, and the other is sensitive to the contrast mechanism of interest. So in acousto-optic tomography, which is what I will discuss today, the resolution is due to the use of high-frequency ultrasound, and the contrast is intrinsically optical, let's say in the near IR, as I showed you in optical tomography. And so it turns out in somewhat sort of operational terms or in physical terms, the idea is that we can exploit an internal control of the boundary measurements by the presence of an acoustic wave. And so let me explain this a little bit more carefully. Okay. So this is a cartoon which is intended to explain the idea of the acousto-optic effect. So the acousto-optic effect actually has a long history. It goes back to Brouillon, who described Brouillon scattering of light from ultrasonically modulated fringes and a gas. Okay, so you can make a diffraction pattern this way if the ultrasound frequency is high enough. But in a suspension of cells or a colloidal suspension, the effect looks rather different. So suppose then we have then a collection of scattering particles, which are indicated here, and we have an incident ultrasound beam, which is here focused to a point and has a frequency capital omega. Well, the ultrasound beam moves the particles around, of course. There are little forces which act on them, little radiation forces, there are pressure forces. And if you simultaneously illuminate the system with light at frequency little omega and detect the light that comes out, then what you find out is some of the light is elastically scattered. That is to say, it comes out at the same frequency that you put it in, and some of the light, in fact, comes out at harmonics of the ultrasound frequency. Okay, so the light that comes out at a harmonic is referred to as shifted or as tagged, and so the idea of acousto-optic imaging, which was first proposed by Claude Bocara about 15 years ago, is to measure the tagged photons, trace them back to their origins, which is the focus of the beam, and then for a fixed optical source and detector configuration, scan the focus of the beam and plot the intensity of the tagged photons. Okay, so that is Claude's basic idea. And the only caveat I will make here is that there are not a lot of these tagged photons. If you look at the spectrum, then what you find out is that the fundamental is much, much stronger than the harmonics. Okay, so this idea is here illustrated by an experiment that was carried out by Li Hong Wang a few years ago. So this is an object of interest, some kind of, I don't know, black balsa wood phantom. It's a sort of millimeter scale, which is already very challenging for conventional optical tomography. And it's immersed into a medium which is scattering like milk. And so if you just take a picture of the light that comes out, a direct image, as Simon said, then this is what you see. It's completely blurred and you don't really know what's inside. On the other hand, if you turn on the ultrasound and you measure the tagged photons, then this is what you see. Okay? So this is, again, just a raster scan of the focal spot of the acoustic beam. Okay? So the resolution here is quite impressive. So what I want to talk about today is essentially a variant of this idea. So what you notice from Li Hong's experiment is that although there is resolution here, it's not so easy to connect this image to the fundamental optical properties of the medium that you want to know. So that is to say, this is an image of intensity, and what you might really want to know is, well, what is the absorption here? Or what is the scattering coefficient here? In other words, you would like to recover the coefficient of a PDE, let us say. Okay? So that is one problem. And the second problem, so that's the usual problem of direct versus indirect imaging, as Simon framed it. And the second problem is that of signal. So in this experiment, as I mentioned, tagged photons are measured, but there are relatively few of them, orders of magnitude less than there are of the elastically scattered photons. So what I would like to talk about is a kind of inverse scattering problem that allows us to recover absorption and scattering coefficients from measurements of the untagged photons. All right? And so this is joint work with Guillaume Ball from Columbia University. Okay, so to make some progress on this, we first have to make a model for how light propagates in a suspension of cells, let us say, in the presence of an acoustic wave. So here is a very, very simple very simple model for the mechanics of such a suspension. So these are the cells, okay? And the physical idea is that in the presence of an acoustic wave, you spatially modulate the number density of those particles in much the same way that in classic Brouillon scattering, you modulate the refractive index, okay? So if you focus your attention on one little particle, of course, it feels a radiation force due to the presence of the acoustic wave, and if the amplitude of that acoustic wave is sufficiently small, then the particle will just oscillate about its little equilibrium position, and you can neglect the effects of all of the other particles on that particle, okay? So that means, in some sense, that you forget about the hydrodynamic interactions in the suspension, okay? So that's a reasonable thing to do if the incident pressure is not very large, and in fact, if the incident pressure were very large, you might disrupt the tissue, and so this is not even a question of real interest for us. Okay, so this is the setup, and then what we want to do is to write the equations of motion for each one of these little particles. And so this is what I've done over here on the left-hand side. We just have the usual F equals ma, and on the right-hand side we have forces, and so the forces that act in this situation are the hydrostatic pressure forces. So this is the force density on the left, rho is the mass density, and this first term here on the right is simply accounts for viscous attenuation of the motion of the particles. Okay, so that's the simplest thing you can do if you have a collection of particles and you neglect their interactions. It's not very difficult, by the way, to perturbatively correct for the hydrodynamic interactions. Okay, so to get a sort of an idea of what's going on here, let us suppose that we have an incident time harmonic acoustic plane wave, which I've written here, so there's wave vector k and phase phi. And then it's easy to solve those equations of motion. So the particles, positions of the particles are simply their equilibrium positions, and then they oscillate about their equilibrium positions, as I've written here. So the oscillation, of course, is inherited directly from the acoustic wave. And now, suppose we have a collection of those particles, then we can write down the number density of them if we know all of the particles. And then now here we have a small parameter, which is really just which corresponds to the assumption that the incident pressure is relatively small compared to some appropriate scale. And so within this regime, we find that the overall number density of particles is just the equilibrium number density that was there to begin with, plus an oscillatory correction. Okay? And it is that oscillatory correction that we're interested in. So essentially what we're doing is putting little stripes, if you like, in the number density in the system. Okay. So that takes care of the mechanics. So now the second part that we have to discuss is how light propagates in the system itself. And to do this, we make use of the simplest kind of model, which is the diffusion approximation to the radiative transport equation. And so that's what I've written here. You recognize it as a cousin of what we had on the first slide. So here d is the diffusion coefficient, which is now assumed to vary from point to point in space. N is the refractive index of the medium, which is also modulated by Brouillon scattering. And this is the absorption in the medium. Okay, and here we assume we have a point source on the boundary. Okay, so how do you compute the diffusion coefficient and the absorption coefficient? Well, they are given in terms of the number densities of the particles and their respective scattering and absorption cross sections. And likewise, in the Brouillon scattering, the number density is also spatially modulated. So at the end of the day, you can put all of this together and you find that the optical properties of the medium are modulated by the presence of the acoustic wave. And you can rewrite this diffusion equation in a slightly more convenient form. So you rescale the energy density by the diffractive index. And here you have a kind of diffusion equation with a diffusion coefficient d and an absorption coefficient alpha, which are modulated, okay, spatially modulated. Okay, so what do? We do the usual thing. To solve the equation, we just write the appropriate Green's function. And here the Green's function is the Green's function in the absence of the acoustic wave, which of course we don't know, right? Because if we knew that, we would know the solution to the problem, which is the problem of recovering the absorption and diffusion coefficients, all right? But for the moment, let's just write the solution to this diffusion equation. So the field psi, which is the renormalized energy density, is just the energy density in the absence of the acoustic wave plus a correction. And this correction has the absorption in the medium in it, okay, and the diffusion coefficient. Okay, so that's the solution to the forward problem. So now we know how to compute the result of an experiment. So what experiment should we do? Well, so we should take a bounded domain, fix an optical source and an optical detector on the boundary, and make a measurement in the presence of the acoustic wave, and then change the direction of illumination, change the wave vector k and the phase. And every time you do this, you make another optical measurement. You collect all of that data and do something with it. Okay, so let's suppose you do those kinds of measurements, both in the presence and the absence of the acoustic wave, and you look at the corresponding integral equation. Well, what you find is that the data that you measure, that's what we call phi, can be related to a function f, which is defined everywhere inside of the medium by this kind of cosine transform, okay? And so by varying the wave vector k of the acoustic wave and its phase, we can invert this Fourier transform, and then we have access to this function f, which is defined everywhere inside. So this is what is sometimes known as an internal functional of the medium, okay? So by doing a number of experiments, we can then put our hands on this internal functional f, which we now assume to be known, and this functional f is related to the Green's function that we don't know, okay, and the absorption coefficient that we also don't know but would like to find, and similarly for the diffusion coefficient, okay? But we have traded off information on the boundary of an optical measurement for knowledge of this internal functional of the medium. Okay, so if I have a point source on the boundary, this is what the internal functional looks like. And let's suppose, as I said before, that it's known from measurements. And initially, for simplicity, let's assume that the medium is not absorbing at all, just scattering. Okay, and so the right-hand side, the second term on the right-hand side disappears. Okay, so we know f, we want to know d, and so we can solve for d in terms of f and the field psi 0 that we don't know, which is the internal field. Okay, but now we know d0, we can plug it back into the diffusion equation. Okay, and we find an equation for psi 0 in terms of f with appropriate boundary conditions. So this is a nonlinear equation, of course. In fact, it's an especially unpleasant kind of nonlinear equation. It's what's called a zero Laplacian. So we have to, in order to get a solution, which we actually don't know very much about, of course we have to assume that this thing is bounded away from 0 on the bottom. But if we could, in principle, solve this equation for psi 0 everywhere, then once we know it, and we know f, we can reconstruct the coefficient d, and that's what we want to know. Okay. Well, just to be a little perverse, I'll show you that it's now possible to recover both coefficients, the absorption alpha 0 and the diffusion coefficient d0, but in order to do that, we require data from two sources on the boundary, and then we get a corresponding pair of internal functionals, okay, which we can now solve for the coefficients alpha 0 and d0 separately, and they now go back into the diffusion equation. This is now, and again, a nonlinear diffusion equation. In principle, solve that for these internal for these fields psi 1 and psi 2, and then once those are known, we can calculate alpha 0 and d 0. Okay? So that is, in principle at least, a method for doing reconstructions. We actually don't know very much about how this behaves numerically, but Guillaume has analyzed the problem a bit mathematically, and I have the following story to tell about that. So let's, for simplicity, consider the case of a non-absorbing medium, in which case we have seen that it's possible to recover d0, the diffusion coefficient, from these internal functionals by solving this kind of, in quotes, p Laplacian in the limit where p is equal to 0. Okay? Now, it's known that the p Laplacian is an elliptic equation for p bigger than 1, and it turns out that it is hyperbolic for p equal to 0. And so that suggests something. So that suggests that you might not be able to recover the coefficient d0 on all of the domain of interest, but instead that we should take the data from a space-like part of the boundary, okay? Just the way you would for the standard wave equation, right? So you recall that for the standard wave equation, it's the space-like surfaces that provide stable initial data to propagate the solution forward, okay? So what Guillaume has been able to show is that within a suitable space-like domain of influence on the boundary, that you can get a local stability estimate, which is very, very nice, right? It's a sort of Lipschitz-type stability. So you can, if you make two different measurements and you measure the difference in H1, then you can recover the difference in D0s within L2. Okay? So that is a much nicer result than, of course, you could ever expect from optical tomography by itself. So there's a real interest at this point in trying to understand something about how to solve these kinds of equations. Okay, so now what I want to do is tell you that some of the same kinds of physical ideas can be used in other settings, and in fact in the settings of inverse source problems. So Simon mentioned the inverse source problem of measuring current sources from voltage measurements, but there are many others. And so this is one in optics. So here you have an animal that has been inoculated with tumor cells, and those tumor cells glow. And as the tumor cells propagate and establish colonies within the mouse over a period of days, and you take a picture of the glowing light, you can see something about where the tumors are. But of course, you don't really know from such two-dimensional measurements what the density of the tumor cells happens to be. Right? It's a classic inverse source problem. You have measurements with not enough degrees of freedom to recover a function of 3 variables inside of the medium. Okay? But I want to show you that by doing a kind of hybrid measurement, that it is possible to make some progress on this. Okay, so what is the idea? The idea is that just as before, we have a diffusion equation, but now we have a source inside of the volume. Okay, that source consists of little cells, and if you turn on an appropriate acoustic wave, you can move the cells around, and so the source also becomes modulated in just the way that the optical properties of the medium became modulated. Okay, so now we can do exactly the same thing. We can try to solve the inverse source problem of recovering this right-hand side by making boundary measurements of the light that comes out. And although this is, as I said, normally not a problem with a unique solution, we'll find that in the presence of an acoustic wave, that changes. Okay, so now you write the solution to the diffusion equation with a non-zero right-hand side. That's the source over here. And actually, that should say S0. It's the source in the absence of the wave, acoustic wave. Okay? And you see, of course, this is completely linear in the source, which is a nice thing and very helpful for us. So if you go through exactly the same kind of argument that we discussed before, you fix the position at which you measure at one position. You measure the outgoing luminescent light at one spatial position, and then again vary the wave vector k in the phase phi. Then you find out that you can get your hands on another internal functional. Of course, you could do better if you measured at more than one position, but for now, let's just discuss this case. All right? So look at what we have. So we have the medium. Sorry, we have the internal functional left that we know. We have the Green's function of the medium, which we now assume is known because we have assumed that we have already measured independently somehow the optical properties, the source that we don't know, and so on. And so if you stare at this for a little while, what you realize is that you can turn this into an integral equation of the following form. So we have the source S0 that you want to know, we have the data M on the right-hand side, and you have identity plus compact. And so, of course, you can say a lot. And so from this kind of formulation, it's possible to uniquely recover the source as 0 if it is spatially modulated by acoustics. Okay, so there's more. You can also think about the same problem now in electroencephalography. So imagine that we have measurements of the voltage on the surface of a patient's head, and here are the corresponding traces that make up the EEG. And the question might be to find the electrical sources in the brain, and those sources might, for example, they might be something like the focus of a seizure, or they might be a more distributed kind of cognitive sources, if you will. Okay. And so what is the corresponding mathematical formulation of this problem? So we have a conducting medium with conductivity sigma. We have a potential field U inside of the medium, and J is the current that flows in the medium itself. Okay? And so this is just Ohm's law, and we have the appropriate boundary condition here, which just tells us that no current should get out. The recovery of J is a classic underdetermined problem. So now we turn on the acoustic field. And what happens is that the charge carriers move. 1 minute, I'm in good shape. Okay? So the charge carriers move. If you know their velocities and their positions, then they undergo a kind of modulation. You can solve the corresponding PDE. And what you find, again, by undoing a Fourier transform and looking at the appropriate internal functional, that you can solve a system of linear equations. A certain number of them are needed, corresponding to a certain number of well-chosen boundary measurements, and then you can recover the coefficient J, which is the source. And I'll stop. Thanks so much.
Hey, so a question or two? I have one.
Yes.
Essentially, what the acoustic modulation does is, in a sense, put sources throughout the medium.
Yes.
And allows you to, or alternatively put, allows you to measure a whole slew of related media.
It does.
At the same time, and that gives you enough information to do remarkable things like solve inverse source problems.
Right. That's essentially how to think about it. So you have some kind of control of the medium, which is imposed by the source, which you would never normally have.
Yes.
And it gives you additional degrees of freedom that, again, you normally don't have.
Right, and therefore additional measurements that really relate to the internal structure.
That's right.
Real quick observation. So just noticing your P-Laplacian equation,
Yes.
I was thinking of the lumped approximation for that, which is a classical nonlinear resistor network
Yes.
problem,
Yes.
which has got some very nice uniqueness theory from the 1950s. So it's kind of interesting that as soon as you approximate that with a lumped approximation, you can use those results.
So I'd love to hear about that. I'm not familiar with any of that work.
And we have the perfect opportunity. We now have afternoon tea. So we'll reconvene in half an hour.